this one. In each of the following, indicate which salt will form the more acidic solution. So we have sodium nitrate or iron 3 nitrate. So let's write these down. Number 1, NaNO3 versus FeNO3. Okay, so let's think of this. Let's look at, we both have nitrates in common. Those are my bases. So let's think about its conjugate acid in both situations, which would be HNO3. Its parent acid, we know that nitric acid is strong, right? That it is not going to have any effect on the pH. So let's just cross those off. Now we just need to compare our cations, sodium versus iron. So let's do this, Na versus Fe, 3+. So let's look at these cations' parent bases. So the cation's parent base would be NaOH. We know sodium hydroxide is strong, right? No effect on that pH. This pH is going to be neutral at 7. Let's look at Fe. Its parent base would be FeOH, iron hydroxide. And we know that it is not strong. We'll call it weak. And so we know that when when this goes through hydrolysis, Fe 3+, in H2O hydrolysis, and it forms FeOH3, it's making those acidic protons. So yes, this is making more acidic. And our question is asking us, which one will form the more acidic solution? Our iron nitrate will. Let's look at number 2, potassium bromide, so KBr versus potassium hypobromite, KBRO. All right, so let's separate potassium bromide into its 2 ions. We've got K plus and Br minus. And here we have K plus and BrO minus. Now let's look at the parent base to K would be KOH. Same with here, parent base, KOH. And we know that KOH is strong. No effect on the pH. So now let's look at these anions. We've got BRO. The parent acid would be HBr, hydrobromic acid. We know that this is strong. No effect on the pH. That means that KBr is going to have a pH of 7.00. It's going to be neutral. Let's look at BRO. The parent acid would be HBRO. And if you weren't exactly sure if that's strong or weak acid, we go back on our Appendix D, hypobromous acid, and it has a Ka constant. So we can see that that is a weak acid. So what is that going to do to our acidity? Well, let's go back and look at the chemistry. If I take my BRO minus and it goes through hydrolysis, then it's going to form, this BRO is going to grab an H, HBRO, that's the parent acid that we just were talking about. And what are we left with? Our water just gave 1 proton away, so we're left with OH minus. So this is going to become more basic. Those hydroxide ions make this more basic. So we've got a 7.0 and we have basic. So which one is more acidic? Our potassium bromide. Let's look at methylamine chloride or barium chloride, see who's more acidic. So methylamine, I think we just did that on the last slide, CH3NH3Cl, and barium chloride, BaCl. So we know that the parent, let's arrange this a little bit differently. The parent acid for Cl would be HCl. And we know the hydrochloric acid is strong. So this is not going to have anything to, it's not going to change the pH at all. I'll just write strong, strong. All right, now let's look at the parent base. So these two, we know that the parent base would be BaOH2, which is strong. So this is going to have a pH, again, it won't affect the pH, we'll have a pH of 7. Let's look at this one, CH3NH3. Its parent base is going to be CH3NH2. All right, now this is weak. And let's look at the chemistry. What happens when CH3NH3 goes through hydrolysis, H2O? That means it's going to lose that, it's going to make that parent base, CH3NH2, that we've just made up here, the parent base. So it lost one of those H's. That means that we have H3O plus. That means that this is going to be more acidic. So if we have a pH of 7 and we have one that's more acidic, it's going to be lower than 7. So therefore, this compound, our methylamine chloride, will be more acidic. And let's look at our last one. We have ammonium nitrite, so NH4NO2, versus ammonium nitrate, NH4NO3. So again, let's look at our parent acids, parent bases. The first one that sticks out to me is this NO3, because we know that its parent acid, HNO3, is strong. So it's not going to have any effect on that. Now, this parent base, NO3, ammonia, we know is weak. And we know that that's going to make this more acidic. Remember the chemistry, we've done that a few times now. One more time, when we have NH4, that's what we're starting with, and it goes through hydrolysis, it's going to form this parent base that we just wrote about, NO3. So it lost one of those H's, and it donated it to water, and so we have H3O plus, which makes this more acidic. So this compound is becoming more acidic. Let's look here. So I have our NH4, which we just said, the base is NO3. It's weak, it's making it more acidic. So I'm just going to copy everything we just did here and write down more acidic. Well, let's look at NO2. Its parent acid is HNO2, which is a weak acid, which is weak. So we know that when a weak acid, or when this NO2, let's look at the chemistry, NO2 minus, when it goes through hydrolysis, H2O, it's going to form that parent acid, HNO2. So therefore, it's grabbing one of these H's, and what are we left with? OH minuses, hydroxide. So it's going to make, this will make it more basic. So this is interesting because this will make it more acidic, this will make it more basic. It's almost like they're counteracting each other. I'm not going to say that it's going to be neutral, but when I have this compound where it's purely making that more acidic, and we're asked which one of these is going to be more acidic, Our ammonium nitrate will, for sure. All right, let's look at our last practice problem. Practice, practice, practice. That's how you're going to get this. So we want to predict whether the salt, sodium hydrogen phosphate, will form an acidic solution or a basic solution when dissolving in water. And it's telling us that it's amphoteric, so it can act as an acid or base. So we're going to need to do both when we're solving this. So sodium hydrogen phosphate, NaHPO4. And this is -2, actually, so it's just Na2HPO4. Okay, so we know that the parent base of Na is NaOH, and we know that that is strong, and that means no effect on the pH. Well, let's look at HPO4. So it just told us that it's amphoteric, so HPO4 can act as an acid or a base. HPO4 as an acid, and we're going to look at HPO4 as a base. So let's say we undergo hydrolysis. So therefore, this water is acting as a base. So when it undergoes hydrolysis, my acid is going to donate its proton. So I'm going to have, oh, and this is a 2 minus, by the way, because of that 2 minus. Here we go. So it donates that proton. So I'm left with PO4 3 minus, which is our phosphate. So this is our conjugate base. And so if it donated that proton, I'm left with H3O plus, acid, right? Good. Now in this case, let's look what our Ka constant is. And it should be on our appendix here. And we're going to look up the Ka constant for HPO4, which is phosphoric acid. Now, phosphoric acid is a triprotic acid. So we know that to lose the first hydrogen, this is its Ka constant, the second hydrogen, and we're trying to pull off the third hydrogen. So our Ka constant to pull off that third hydrogen, which is what we just were doing, pulling off that last hydrogen, is 4.2 times 10 to the negative 13. Now let's do equation number 2. Looking at HPO4, 2 minus as a base. When that undergoes hydrolysis, so this water is acting as my acid. That means that this, if my acid is a donator, so this will become H2PO4 minus. This is my conjugate acid. And what am I going to be left with? OH minus. So again, we look at this and we go, ooh, well, it can produce, if this HPO4 acts as an acid, it will produce hydronium. If it acts as a base, it's producing these hydroxides, the conjugate base. But how do we know which one's stronger? Well, we need to find this K constant. In this case, though, we're going to be finding the Kb value. And how do we find the Kb value? Well, remember that expression that Kw is equal to Ka times Kb? So we know Kw is 1 times 10 to the negative 14th. We know our Ka value is 4.2 times 10 to the negative 13th. So our Kb value, if we plug this into our calculator, let's do 1 times 10 to the negative 14th divided by 4.2 times 10 to the negative 13th. We get a Kb value of 0.024. Remember that slide that said if the Kb value is greater than Ka, so here's our Ka, here's our Kb, which is a greater number, 0.024 or 4.2 times 10 to the negative 13th? Well, in this case, we have our Kb is much greater than Ka. So Will it form an acidic solution or a basic solution? Definitely a basic solution. At this point, you have done a great job. You have finished with me looking at how Kas and Kbs are related. You have also practiced the hydrolysis of salts and using those values to start ranking pH of those negative and positive ions. This concludes the lesson. Your notepad is now filled down towards the bottom of the page.